invite the speakers. So there are 4 eminent speakers who will be talking on the future proofing of supply chain, and you'll find that the topics they have chosen will cover wide variety and wide range. So there will be batteries, there will be clean technologies, then there will be industrial metaphors, and I hope you'll all enjoy the discussions. So I will invite Saksham Gupta of Kamtech Associates to come to the podium.
Good afternoon, everyone. This is Saksham Gupta. I'm the director of Kamtech Associates. Today, I'll be talking about how integrated digital twins are enhancing efficiency and collaboration in the industrial metaverse. Starting on. So, a small introduction. Kamtech is a turnkey project management consultancy company. We are a 20-year-old company working across various domains, sectors for end-to-end project execution. We are also working with European companies to help them expand in the Indian market. One such company is Framens. So Framens has created a platform to create 3D photorealistic digital twins. And this is a German-based company, I'll be presenting how Framens can really help industries, make their operations smarter. So a big problem across industries is that when you have locations or your site locations across different geographical locations, you need specialists to travel on the site for gathering maybe location information, for monitoring changes, progress, and that usually results in about 20 to 30% of loss of working time, which also results in loss of revenue, increased downtimes, reduced margins. To solve that, we have Framens. So Framens essentially makes such trips completely obsolete. The digital twin solution offers a very Google Street-like view for your factory, building, or technical installation, and all of that with centimeter level accuracy. So what you see in the picture is a picture of a shop floor. Usually there is a digital twin of a product where, of course, you can create a virtual replica of your product, in this case the car, and get insights or data-driven to make data-driven decisions. Then comes maybe your system, your facility. You can also create a digital twin of the process or the asset. With Framens, we're able to create the digital twin of the entire industrial facility. That includes your product, your assets, as well as the entire industry. Thus, offering very efficient facility operations and maintenance. So how we do that is that we digitize all the physical structures and assets within the factory. We create virtual photo replicas of the buildings and the facilities, and we can do that with cutting edge precision. So you can literally measure from point A to point B anywhere in your plant between maybe 2 pipes if you want to get the distance, and we can do that with centimeter level accuracy. The third one, that of course you can see real-time asset information. If you have any sensors, IoT devices, you can read and see the real-time the stats in the factory using the digital twin. So Framens offers a single point access for all the data that you have, whether it could be the asset information, it could be plans, it could be process data, it could be your IoT sensors data, it could be any videos, content that you have. The 3D models, all of these data points can flow into Framens within your virtual digital twin, and you can access this information over a period of time. So if you want to go back, let's say maybe if you want to see 3 months back, what was your assets, what was the kind of data they were producing. If you want to see all that information, you can go back in time and check, compare, so you can get quick results and more insights. So what we do with Framens is that we use mathematical functions and artificial intelligence to turn simple images taken from your phone, DSLR camera, your mobile phone, or even your drones. We can convert those photos into centimeter accurate photorealistic twins. And you don't need any expensive hardware or any expensive kind of equipment to do that. It's quite simple. And even if you want to update your twins later, all you have to do is take out a smartphone, take pictures within your facility, and you will have the updates done. Moving on. So I would like to show a small video to demonstrate how a digital twin of your industry or facility could look like. So that's how you can go to your like on-site in seconds. What you're seeing is basically the digital twin of an industry. As you can see, it's quite detailed. You can zoom in to see accurate results, even the asset number. You can navigate within your facility very easily. You can also superimpose floor plans into your 3D model, so you can compare as built versus your current system, which makes it very easy. And also the assets that you see, you can convert them into 3D models as well. What you're seeing here is live. You can measure the distance between any 2 points, and this is literally centimeter level accuracy. So it's highly accurate. You can plan if you want to set up something new or make changes in your existing industry. You can see, you can even control devices through actuators within the facility, and you can see real-time data like you were seeing for the pump, the numbers, and you can even see the charts. All of that while sitting remotely wherever you are. So there are a variety of use cases of this digital twin. You can use that for asset documentation. So I mean, in any industry facility, you could have thousands, of assets. With Framens, we can document all those assets. You can add annotations. And you can easily look each of those assets up. It will exactly locate where your asset is. You can access the information within the asset with using IoT or sensor data. You can use it for maintenance and repairs. So of course, we can also connect this with augmented reality. So if someone wants to do maintenance and there's a regular system of how to do maintenance, we can add that information as a layer and can be projected over your physical plant. So if someone is using a tab and looking around, they will see, okay, what steps they could follow. That could also be done just with the digital twin. This can also be used for visual construction documentation. So if you are running a construction site and you want to see how it has progressed through time, you can easily monitor the past and the changes, and also superimpose floor plans to see the progress. Like I said, you can compare as built with as planned drawings. This can also be used for converting photos into precise 3D models for building information material. And you can import these models directly into CAD systems. This can also be used for brownfield planning. So if you have an old industry and you want to, sometimes just because you're revamping that, you want to see how exactly where new systems could flow, where new machinery could go. So you can do the entire planning by first, creating the digital twin and then seeing how you could roll it out. So how the whole process, how we make Framens really easy, that it's very easy to install. The installation needs, as I said, it's just images of the facility to create the digital twin, no high-end software. The whole process is very cost-effective to first set up and then to even run long-term compared to the competitors. It also offers, in case you have already invested through using maybe 3D scanners or any such photogrammetry if you have done of your facility, we can actually leverage all of that data and put it into Framens so that you can save on your investment. We can connect to any third-party systems, whether that you already have, and get their data directly into the Framens portal. And you can, of course, search through all your assets within the platform. Yeah, thank you. If you have any questions, please let me know.
So you just have a very nice presentation on industrial metaverse. Actually, when we think about industrial metaverse, we know that it is a very, very futuristic technology. Like we talk about IoT as Internet of Things, and metaverse is called, which is a much bigger thing, it is Internet of Twins. So which is a bridging the gap between physical world and virtual world. So now we'll go to the next topic. It will be by Indrayuth Mukherjee. Indrayuth, please come to the podium.
Good afternoon to all of you. I hope you're all enjoying the India Energy Week 2024. My name is Indrayuth Mukherjee. I am an associate director at the Clean Energy Technology team at S&P Global Commodity Insights. I think my topic for today is clean power supply chains, keeping pace with global demand growth. We are ultimately an information company and we track the clean energy technology sector very closely. So today I was kind of hoping to take you through a session where we talk about clean energy technologies, what's happening at a global level, what are the technologies that are being installed, where is the growth coming from, also what does the manufacturing look like, and how does India kind of fit into the picture. So I know that's a lot, but let's hope to cover all of it today. All right, I think starting off, first things first, let's take a look at the high level message. The high level message is that the energy transition is accelerating. The recent COP28 targets a tripling of installed renewables capacity to almost 11 terawatts by 2030. And what we're seeing, or what we're estimating, is that the annual additions for clean technologies will nearly double by 2030, and doubling, it's a big deal. If I have to put that in numbers, in 2023 we had roughly 550 something gigawatt that was installed. By 2030, that is going to be north of 900. In terms of investments, in 2023 we had, I think, $600+ billion. 2024 we are looking at roughly 800, and by 2030 we might just hit the $1 trillion mark. In terms of what technologies are being added, well, you can already see there's a huge orange bar over here, which means that the domination is going to be by solar. This is not a surprise because solar remains the cheapest, quickest, and easiest to install technology. This is going to be followed by onshore wind, increasingly by offshore wind. There's also going to be a lot of batteries and energy storage systems, because as you add so much of intermittent capacity to the grid, you also need something to kind of balance your power systems. And as well as, towards the end of the forecast period, we're going to see more additions of decarbonization technologies like green hydrogen, which is going to be produced through electrolyzers from almost nothing right now. Now, if we take a pivot and kind of look at, okay, where are these additions going to happen? Well, 1/3 of it is going to happen in China. The other 1/3 is going to happen in what we call the developed Western markets. So we're looking at Europe and the US, and the remaining 1/3 is going to be spread out all over the world. If you think about India's position in this whole thing, India is going to be roughly 5 to 6%, which is by no means a small thing. And as far as where it's going to be used, then most of it is utility scale power. Some of it is distributed, not some, 1/3 of it is distributed. When you're looking at distributed, it's mostly just solar and batteries, and the remaining is going to come from hydrogen production. But let's kind of take a step back, okay? So clean energy technology additions are going to double between now and 2030. Clean energy technologies, they run on wind, they run on the sun. There is no variable cost involved. But if you really have to double the amount of capacity that you need to add, it's obviously going to require a significant response on the supply chain, because we all want cheaper electricity. We want the cost to fall, and the costs falling, a lot of that is dependent on the manufacturing side or the supply chain side, right? So, if we think about how much each of these technologies, need to scale up in terms of additions, for mature technologies like onshore wind, solar, we're looking at roughly 1.2 to 1.5 times. For something like energy storage, which I won't say is new, but it's still new compared to the previous two, we're looking at somewhere around 2 times. But for technologies that are much newer, for example, offshore wind, we're looking at a 4 times scale. For something like electrolyzers, we're looking at roughly a 7 times scaling. Is this a problem? Well, if the world was truly globalized, ideally it should not be a problem. What you then need to do is find out where the manufacturing is happening today, where it is cheapest to manufacture. The answer to both is China. And then what you do is you kind of scale up your manufacturing in that location and export it to all of the other markets. So everybody gets cheap electricity, everybody gets cheap components, it's all getting manufactured in one place. But unfortunately, that's not the world we live in right now. So, the geopolitical tensions across the world are quite high. In the Russia-Ukraine crisis, we have seen the problem or the possibility of weaponizing energy. And now what we're seeing is more of these markets want to have localization of their supply chains. They're not comfortable importing everything. They want to produce at home. They want their supply chains to be also located at home. And this kind of creates a problem or a challenge, I would say, maybe not a problem. The challenge is, can you realistically produce everything everywhere all at once? And can you also do that in a cost-effective manner? And this is something that the supply chains are increasingly going to face, and that's a challenge that they're going to have to reconcile with. But why do I say this is a challenge? I think this map to that is quite interesting. I think if you remove everything and cut through the data, what it basically tries to show is where is the manufacturing for these different clean energy technologies at a downstream level. So downstream means module, turbine. So at a downstream level, where is the manufacturing for each of these different technologies? The bars represent the share of global manufacturing, and the colors represent which technologies these are, right? And immediately what you're going to see is there's a significant domination of mainland China in this entire picture. For China, clean energy technology is a very key growth engine. They want to use that as a way to power their economy. They want to be a dominant player in the export markets. They want to supply a lot of the clean energy technology equipment that we're using today. And which is why we see a very dominant share that they have right now. But at the same time, it's not that they're just scaling up the technology, but the technology itself is also getting better. We're also seeing a movement from, let's say, P-type to N-type cells. We're seeing a gradual interest in moving from lithium to sodium ion, which one of my colleagues will talk about slightly later. But there's also a technology shift that's happening. So all of that is kind of coming out from China right now. But in the end, what we are looking at here is still downstream, right? And when you're thinking about downstream, this is still something that's easier to localize. It's easier to localize an assembly of solar panels if you can import all of the subcomponents from somewhere else. It's easier to assemble a turbine, if all of the subcomponents are coming from somewhere else. But when you're looking at something like clean energy technologies and the equipments, it's not enough to just look at the downstream level of things. We also kind of need to move to the upstream level of things, right? Is that, okay, you're assembling a battery here, but where is the material for all of that battery going to come from, right? And that's why when we move into, and that's why when we kind of move into more of the upstream side of things, you see kind of a different picture here, right? So what you're seeing here is, two things. So firstly, we're looking at the raw materials that are required for different clean energy technologies. So you're looking at things like lithium and cobalt for batteries. You're looking at silica sand for solar. You're looking at rare earth elements for wind turbines. You're looking at aluminum and copper that is used almost everywhere, right? And we're comparing it in two axes. So we're comparing the extraction or the mining, and then we're comparing the processing. So if you're looking at the extraction side of it, it's not that problematic. We do have reserves for all of this spread out all over the world, right? So for example, cobalt might be coming from the Congo, or lithium might be coming from Australia or Chile. But when you move your attention to the right side, that's when things start to get a bit problematic, because when you're looking at processing, it turns out that the domination that we have on the processing side of things is almost exclusively coming from mainland China. And processing is a very important part of the puzzle, because this is where you take a raw material and then you kind of add value to it and basically transform it to something that can then be consumed by the supply chain. So, this is a value addition step. This requires a lot of scale. The initial investments are going to be very high. It's very power intensive. It's also very labor intensive in nature, right? And where that brings us is, it kind of begs the question, can you really have fully vertically integrated supply chains spread out all over the world, where you're processing and extracting materials and then, building everything in your country? And, is that really going to be cost efficient? And can you really do that while keeping your labor standards and your environmental standards also intact, right? So this is quite, I would say, a big challenge. And to that extent, I would say India kind of fits very nicely into this picture because we do have a low cost position. So, we're going to explore what India is doing on this front, but, this is what the supply chains in general look like. But, we've seen what the supply chains look like. So, just to kind of recap what we've been seeing in the last 4 slides, investments are growing, capacity additions are growing. At the same time, there is a growing call for localization of clean energy technology supply chains, but localization is going to be challenging because a lot of the manufacturing is happening in China, and at the same time, it's not the downstream level, but a lot of the upstream dependencies are also in China, right? But what are we seeing now in terms of actual manufacturing capacity? And I can tell you, and maybe all of you are noticing the prices of batteries, or you're noticing the price of solar modules, and you know that it's going down very fast. And basically what we're seeing is over the last 2 years, over the last 1 year, what we're seeing is that there's a huge amount of new manufacturing capacity that is getting added across the world at the downstream level, and a lot of that is also coming from China. So just to give you an example, we are tracking roughly 300 gigawatts of module manufacturing capacity that is going to get added globally, and roughly 130 plus gigawatt hours of energy storage system capacity. And this is equal to the total demand for all of this in 2022. So what happens when so much supply hits the market? It's going to push the prices down, and you can already see the line, that's the average selling price, that's starting to come down. Is this a problem? No, we all want clean energy, right? And we want it cheaper. But the problem is there are different policies across the world which are saying we want to have this localized, right? We want to produce modules locally. We want to produce batteries locally. But if you have so much of cheap supply flooding the market, what's going to happen to your localization incentives, right? On one hand, in Europe, what we're seeing is that a lot of the planned capacity is kind of on hold right now. In the US, we have the Inflation Reduction Act, and that's a huge subsidy, right? And that's kind of leveling the playing field. But we also have to understand that as the costs keep going down, your subsidies are also going to keep increasing. And 2024 is the year of the US elections. So that's a very interesting dynamic that we kind of need to understand. But where does India fit into this whole picture, right? If we look at solar, India, solar is very strategically important for India because solar is going to account for roughly 3/4 of all of the clean energy technology capacity additions that we expect in India. So India is roughly a 27 gigawatt DC market that is expected between now and 2030 for solar, roughly 5% of the global additions. And this is significant. And India does not want to import all of its panels. India wants to be self-sufficient in terms of manufacturing. And in order to do that, what India has done is, not just self-sufficient, but also kind of position itself as an exporter. And in order to do that, what India has done is it's kind of taken a triple approach, or a triple lock approach kind of thing. So one part of the approach is a penalty, one part of the approach is a restriction, the last part of the approach is what we would call an incentive, right? So if you look at the first part of the approach, that's a penalty, then that's called the basic custom duty. That's roughly 40% on modules. Even at the cell level, I think it goes down to 25%. But what it basically says is if you're going to dump Chinese panels in India, it's going to come at a premium, right? You can already see that had started to work. So when we basically implemented this in 2022, there was a huge fall in module imports right after. And then the module imports remained pretty flat afterwards. But, don't read this literally, because before the BCD was kind of implemented, there was a huge amount of stockpiling that was happening. So a lot of the additions that happened in 2022 were also driven by these stockpiles. In 2023, we're looking at a different picture, and that brings me to the second side of the puzzle, is your restrictions. And in India, we have something called the approved list of models and manufacturers, or what's called the ALMM. And that's also a second way of kind of blocking a lot of imported supply of modules coming into the market. The problem is that the ALMM has a moratorium that's going on for 12 months. So, the ALMM is not valid till the 31st of March 2024, which means you can still import panels, which is why by September 2023, when the global prices of modules had come down, we're already starting to see a spike in imports. And once we get the data for October, November, December, etc., I can tell you that these levels are going to be higher. But if the ALMM does not get extended, then that's kind of a mandate for you to procure domestically. But ultimately, we need to also understand that, okay, you have a penalty, you have a restriction, but India also needs cheap solar, right? And we need a lot of it. So there also needs to be some incentive that's going to basically say, okay, manufacture more locally. And the instrument for that has been the production linked incentive scheme. We're already seeing there have been 2 rounds of the PLI, and what we have seen is there's a lot of interest in setting up of new manufacturing facilities. A lot of that, or most of that, is in the module level, or what we call the downstream level. But as well, what we're also seeing is that, and that's a great news, is basically the PLI is not just incentivizing manufacturing at the module level, but it's trying to do that across the value chain. So polysilicon, wafer, cell, things where China has an absolute dominance in, right? So we are having a lot of these new manufacturing capacities that are also planning to be integrated in nature, which is going to manufacture everything in the same factory. And we're keeping a close eye on, so some of these projects have had their hiccups, but the others are scheduled to come on track. And what does that mean for our self-sufficiency? Well, if all of this comes online, in addition to what we already have, then we're going to be not just self-sufficient, but it's going to be a net positive thing. So we're going to be basically exporting a lot of that, as you can see from the chart on the right, where the self-sufficiency line is red and then everything is on top of that. The main problem is, if you look at modules or if you look at cells, in terms of theoretical manufacturing capacity, we already have a lot of capacity in India. But the problem is this is slightly outdated. The utilization rates are not that good. And we're using a lot of this capacity to kind of export to the US predominantly, which is why most of this new capacity that's going to come online might kind of change the dynamics of cost. And with the support of the custom duty plus the ALMM, it's we expect that it's going to actually drive more domestic consumption of locally made modules. At the same time, I think it's also interesting to look at wind, because onshore wind, that comes right after solar. And we're even planning a 1 gigawatt tender for offshore wind as well. So wind, it's not as huge as solar maybe, but it's still a 4 gigawatt per year market, and it's still going to be important. But the wind story is very different from the solar story. The solar story is different because you can mass manufacture solar modules, you can put them in a truck, you can ship them to wherever you want, and then you can build stockpiles. But wind turbines are huge pieces of equipment, and it's not possible to mass manufacture wind turbines and just stockpile them. So the wind turbine supply chain is also kind of dependent on your order intake, right? And basically what we're seeing here is that we have sufficient supply, actually a 4-time oversupply of wind turbine components across all nodes in India. But it's not just the oversupply that is important. What we need to know is who owns this capacity, or who owns the wind turbine manufacturing capacity. So when you think of wind, you can kind of divide the global market into 3 phases, right? So one part of it is what we call Western turbine manufacturers. And what is a Western turbine manufacturer? I think you've heard the names of the companies: Vestas, GE, Nordex, Acciona, Siemens Energy, etc. These are companies that supply almost everywhere in the whole world, right? Then you have your Indian companies like Suzlon, Inox Wind that are supplying domestically. And then you have your Chinese companies that are mostly supplying in China, but similar to solar and similar to batteries, they also have a low cost, high production, and now they also want to expand to international markets. What we see here is kind of encouraging, because what we're seeing is that the Western turbine manufacturers actually have the highest manufacturing capacity in India. And that's important because these companies are not just dependent on the local activity, or they're not just dependent on India demand to kind of move their supply chains, because they're supplying all over the world. Which is why in 2020, when the supply chains for wind were shutting down all over the world, in Europe, in the US, in India, what we saw was an expansion of supply chains. And a lot of this has been spearheaded by the Western companies. And what they're trying to do is kind of prime their wind supply chains in India as an export hub. But we also need to be cautious, because while there seems to be a lot of overcapacity, not all of the wind supply chain in India is actually meant for exports. What does that mean? For example, an Indian OEM, they do not have any international orders. If you do not have an international order, you cannot export your turbine. Similarly, in the Western, even for the Western OEMs, wind turbines, you're looking at a 100-meter blade or a 70-meter blade, right? If your factory is located inland and it's not close to a port, it's not really feasible to kind of ship everything to a port and then export it, right? So you also need to kind of look at where this capacity is located, and not all of the capacity that is located right now in India is optimally situated for exporting. Even so, we've kind of identified some of these hotspots. So for example, Tamil Nadu, which has one of the largest wind install manufacturing capacities, is actually expected to be a very strong exporter as well. For example, a company like Vestas, which is the largest manufacturer of wind turbines in the world, has actually scaled up their operations in Tamil Nadu. And they're looking to use that as an export hub. And even specialist manufacturers like TPI Composites are looking to do the same. So in the end, I think in order to summarize it, we're seeing a double side of the world here. On one side, we're seeing a lot of additions of clean energy technology, but we're also seeing a lot of the domination of the manufacturing of that coming from China. But at the same time, every country now wants to relocalize, they want to reshore, but if they cannot reshore, they also want to friendshore. That's also a term that we're now using. And this kind of opens up an opportunity, and India is very uniquely positioned to that extent to kind of capitalize on that. And they're already starting to do that for solar with a multi-pronged approach, which includes penalties, blocks, as well as incentives. And also for wind, where they already have a very self-sufficient supply chain. And what they're now looking to do is kind of prime that up for exports and kind of leverage their manufacturing superiority to kind of supply to export markets as well. I know this was a lot, and we went through a lot of different things. I'm happy to take any questions, and or if you don't have the time, just reach out to me separately. We do a lot of research on this, and this is just a very high level part of that. I hope this was helpful. I hope you enjoyed it. I hope I did not bore you, and thanks a lot.
Thank you, Indrayuth, for an excellent presentation. And he started the story at the very right slides. As we know, the 5-point plan for India's net zero journey, which was declared in COP26, the 4 points are targets set at 2030. So which was presented in his slides. The 2 of the points are related to non-fossil fuel energy and renewable energy targets. So that makes 2030 very important. And another important thing in his slides, he has given the picture, the very clear picture of the world clean technology positions and the country-wise and region-wise. And also another very important factor what has come out of his presentation is the dominance of China. And that dominance is not only restricted in clean technology. If we see robotics, if we see artificial intelligence, if we see e-vehicles, so China is number 1 or 2 in all of these. So India has also a lot of potentials, as we have shown in one of the slides. And there we have shown that there is a huge potential for India in the energy storage or batteries. Because if you see the India's contribution in the world in the batteries is very low. So with that in mind, our next presentation will talk about that. Please. Ritesh Mittal is not present, so the 4th topic will be presented now.
So, good morning, one and all. Hope my voice is clear. Presentation, please. Well, then we'll start with just without the presentation. So, I'm Dr. Binitha. I'm from Hindustan Petroleum Corporation Limited. I'll be discussing about need for batteries and our improvement or our work effort on development of a high voltage fast charging sodium ion battery cathode material development, and which is for an affordable sodium ion batteries. So prior to that, I'd like to thank my previous colleague who has set the right tone on giving the discussion about what is the need for energy storage and what is the penetration of the clean energy and what exactly is the Chinese dominance on that. So further moving on to the content, I just want to first discuss about my organization. As I told, I am from Hindustan Petroleum Corporation Limited. We are actually a Maharatna company. We have 3 refineries, one in Mumbai, one in Vizag, and the upcoming one in Rajasthan refinery. And I am assigned as a assistant manager in our exclusive R&D center, which is in Bangalore. And our core purpose is actually to make the energy and chemicals accessible to everyone through innovation. So with that, I just want to tell you one thing. We have an exclusive stall, which is actually in the entrance of Hall 2. If you have time, just have a visit over there so that we can discuss about the different facilities or the different work which we are doing over there. And we will be happy to discuss in detail on that. Okay. So further moving on to the content, first and foremost is a brief introduction about energy storage devices, which is mostly the lithium-ion batteries. And just like my colleague was mentioning, what is actually the requirement for a future-proofing the supply chains. So further, a potential alternative for lithium-ion batteries, which is actually sodium-ion battery, and our effort on indigenized development of battery materials and its performance characteristics also. And finally, conclusion and the future prospect in that regard. Okay. So coming to the introduction, just like everyone know, we are actually in an era where the demand for energy is increasing. Currently, almost all our requirement has been met by the fossil fuels, but there is a strict restriction on the global climatic changes of the temperatures, which is going to increase, or the net zero, which we want to have. So in this regard, right now, just like my previous presenter, Ms. Indrayuth mentioned, we are more onto solar and also renewables. So in this regard, if you have mentioned that just solar can't work because it is intermittent source of energy. The sun won't shine all the time, or the same way the wind won't blow all the time. So in order to make it a continuous supply, it should have an energy storage device. And if we consider this energy demand or the energy storage device, especially rechargeable lithium-ion battery, which is actually the prominent sector or the prominent potential storage devices, and we have an estimate of almost 150 billion by 2030 with an average growth rate of close to 5%. So if we consider just like this rechargeable batteries, what I was mentioning, the lithium-ion battery is actually dominating the market. Maybe I can 100% sure that at least all of you will have at least one device which is powered by a lithium-ion battery. Either it would be a mobile device or a laptop or any other portable devices like watches or even an EV. Okay, so considering these facts, like why lithium-ion battery was important is that it has very specific features. Just like it has a high energy density, excellent cycle life, low self-discharge, and also low maintenance. So considering all these properties, it dominated the sector, and even it is penetrated even to the Indian market, especially in the forms of not just EV vehicles, even other portable devices also. So though the technology is at its best, actually the dominance is just like he was mentioning, it is almost in the Chinese sector. And there are some basic things which I want to consider because we have a diverse audience, and I just want to quickly introduce about how actually a lithium-ion battery works. So this is just a schematic illustration which has been shown over there, wherein as you could see, the primary components are called anode, cathode, and the electrolyte. In the next figure, you can see the components of a battery, wherein it will be like cathode, anode, current collectors, which will be typically metallic in state. There will be an electrolyte, which will be allowing your ions to pass in and out. And typically for lithium-ion battery, it's a lithium ion. And there will be a separator, which will be a polymeric membrane that will prevent the short circuiting from the anode and cathode. And some cases which to hold that whole components. Okay. So during actually a discharge, the lithium ions, as you could see from the schematic, it's moved from the anode to cathode, which is followed by the movement of electrons through the external circuit. On discharge, exactly opposite happens. And this will be used to power the device for further future applications. Okay. So considering these factors, when we see about the components of the battery, the main thing which we want to find out is actually the major share of the price comes from the material, which is actually the anode and the cathode. And if we consider the different materials being explored for lithium ion battery, you could see that there are numerous materials or myriad of material being evolved. And in that, actually the most prominent ones do have components like either lithium or even just like shown over there, cobalt or nickel. So these all do have restrictions, just like mentioned, the Chinese domination is over there. So considering these factors, though we are saying as if it's the best, there are some limitations and we should have to future-proof this supply chain. So the basic limitation is, first, there is a fire issue, the materials being used are toxic, we have a supply chain restrictions, and there is some design limitations also. So among all these, the main problem or the main concern which we Indians has to think about is actually the supply chain. Just like my colleague was mentioning, we do have, the Chinese market do have different metal refining and also processing. But the main thing which I want to tell you is, though he was mentioning as if China doesn't have much of a lithium reserve, actually the mines which is there in Australia, Chile and Bolivia is majorly owned by Chinese people. So that concern is there. So though they don't have the reserve, they have that hold on to these structures. So not just on these materials like lithium, rather on other components like cathode, anode, electrolyte, and even the separators. These are being dominated by the Chinese market. And along with that, recently there is a Chinese restriction on graphite import. So graphite, this material is being typically used as an anode for lithium-ion battery. And if we don't have graphite, maybe the lithium-ion battery doesn't even work. So recently what happened, this Chinese have imported, banned a small restriction onto graphite import, wherein they do have good hold on to natural graphite and also synthetic graphite. So in natural graphite, they own almost 79%, and in synthetic graphite, the dominance is almost 100% because it's 97%. So considering all these facts, a possible alternate where India can think about is actually sodium-ion battery. So maybe I can mention as if sodium, as you know, the reserve is plenty. It is almost 2.6% on the Earth's surface, and its raw materials will be pretty inexpensive. And along with that, the current collector, which I was mentioning before, for sodium-ion battery, we don't need copper current collectors. It's just aluminum, which is in fact a cheaper option. And along with that, there will be a better safety characteristics for sodium-ion battery, mainly because this can be transported even at a lower temperature. So such kind of designs are also there, wherein the transport restriction for lithium-ion battery won't be there for sodium technology. So in that respect, as you could see from the right side, considering all these factors, there will be a reduction in the material cost also. Why? Because anyway, the components will be inexpensive, and also there will be less current collector, which is in fact, in other ways we can mention there will be 30 to 40% reduction in the price of this component. Okay. So another interesting thing is that this sodium-ion battery technology is actually a drop-in technology, just like the lithium, wherein all the equipment which has been used in lithium-ion battery can be used for sodium-ion battery. So this is just like lithium-ion battery gigafactory can be retrofitted for a sodium-ion battery technology. So equipment, there won't be any change. It will exactly remain the same. In along with that, you should mention as if these are on par with lithium-ion battery. So there's a more chance that it can be used for low-speed vehicles, even EV. And along with that, it can be definitely be used for large-scale energy storage. So considering all these factors, in our HPCL, we have put a humble effort in order to make our own cathodes for sodium-ion battery, which is in fact the indigenous development of battery materials. So in that, what we have done is, we have selected a particular cathode material, which is a polyanionic compound, which is sodium-based fluorophosphate, which does have a higher theoretical capacity close to 130 milliampere hour per gram. So another interesting thing about this material is, typically lithium-ion battery materials will be having an average voltage of 3.4. But interestingly, this material do have a high voltage, which is close to 3.8. It's greater than 3.7, I'll say in the average way. And it do have some stable profiles. So as you could see from the figures over there, it has the capability to move out sodium out of the structure. So actually the sodium which is in the structure is a indirect relation of the how much energy it can be stored. So in that respect, it can take 2 sodium, giving a capacity close to 130 milliampere hour per gram. So there is always a positive and a negative. So in this regard, actually this material do have a big problem. The first and foremost issue is a conductivity problem, and the next is actually expensive synthesis technique. So just like the issue is every researchers will come up with their own solutions for that. So we do in R&D, we came up with a solution which is actually a simple fissile and a fast hydrothermal technique which doesn't need a post annealing process. So this kind of materials, it has to be highly crystalline in order to transfer the sodium in and out of the structure. So rather than having that high temperature annealing, we have tuned the process in such a way that it doesn't need such an annealing temperature or post annealing process. Rather, we can go directly from a bulk scale or a gram scale to even kg scale in our lab level also. So we have even investigated using local chemicals for the synthesis, and we have concluded that the material is on par with sodium and battery cathode price. So there is a scope for India to develop such kind of a material. So further, we have characterized this material and it is crystallized perfectly. You could see from the XRD, and the particle size are almost in the range of 100 to 120 nanometers, which is perfectly for our particular applications. And further, coming to the electrochemical performance, which is actually the sodium and battery performance, from the image you could see the average voltage is very high. This is actually a voltage versus specific capacity plot, which is a battery performance characterized, wherein you could see this material is giving a capacity close to 112 milliampere hour per gram at a C rate of C/5. So C rate means how fast your battery can be charged. So this is a typically slow charging, which is 5-hour charging and 5-hour discharging, giving a capacity close to 112, and you are having a first cycle Coulombic efficiency close to 90%. So that is a pretty high value. And this has been even tested for different rates starting from C/5 to 2Z, wherein 2Z means half an hour charging and a half an hour discharging, which means that it's kind of a fast charging material. And we were able to get a capacity close to 78 for almost 1000 cycles. So cycling stability is also high, which means that if you use a battery, you should want to use it for longer cycles. So more the cycle number, better will be the battery material. So as a result, I can conclude as if it's a high capacity material, or the material which we process is high capacity with a decent rate capability. It was giving 2C charge and discharge. And further, to improve this performance further, what we have done is, we have gone for a carbon incorporation. Maybe I'll show the details. So the carbon which we have gone, being a refining company, we were interested to utilize or valorize a carbon which is part of our another technology called HPHCNG, which is Hindustan Petroleum Hydrogen Enriched Compressed Natural Gas. So here in what the technology, this is actually a commercialized technology wherein we have done a pilot kind of a study also, wherein what they have done is they have taken natural gas and it's been processed in this particular reactor with particular catalyst. It will end up with HCNG. Along with that, there will be some carbon. So this carbon is actually a carbon nanotube. So in order to valorize this carbon for energy storage application, what we have done is we have incorporated this carbon with our material, which is our sodium polyanionic compound, and we got a patent for this technology, and it will be an additional valorization of the same thing. So in that regard, what we have done is you can see a comparison of the data which is with carbon nanotube, which is the modified NVPOF. We could see at different rates. You can see from C/5, C/2, 1C and 2C, there is a significant improvement in the performance, which means that because of the incorporation of CNT, your rate or the fast charging capability is getting improved. You can see almost 1.5 times improvement in the rate performance, especially at a fast rate of 2Z. And you could see even the profile is very flat, giving a voltage range of almost 3.8 volt. Additionally, the same has been cycled for almost 1000 cycles with a retention of close to 96%, which means that your loss is pretty minimal even at the end of 1000 cycles. So this is a humble effort which we have done. On conclusion, what I want to tell is, we have to have a future-proof supply chain in order to develop a proper technology. Though we have the material, doesn't mean that the supply, if we doesn't have the supply chain, it will be very difficult to come up with a proper solution. So in that effort, we have developed a cathode material via economically viable, scalable technique, and we have scaled it up to kg scale also. And the performance is improved further by a carbon incorporation, which is even developed by another process which has been developed our R&D center itself. and this was shown to have a higher voltage, higher rate capability, and also long cycling performance. I'll be happy to take any other questions if you have. So thank you so much. Thank you, Chair.
Thanks, Binitha, for the nice presentation on sodium-ion batteries. So as you have highlighted that with high energy density, this will be a very good alternative of sodium-ion batteries. And as you know that in India, presently we do not have that supply chain, but one of the global battery manufacturers, CAPL of China, they have started manufacturing sodium-ion batteries. So we hope that in India also there will be scope for utilizing this type of batteries very soon. So now I will request all the speakers to please come to the seat so that in case of any question, you can take the questions from there.